of Physics in Action. I am your host, Miss Nielsen, and today we are going to continue building on our foundation of physics knowledge. Last semester, we learned all about the motion of objects. We learned that objects can travel at a constant velocity, and the reason why they do so is because all of the forces acting on those objects are balanced. We also learned that objects can accelerate, and today we are investigating why. That's right, folks. Today we are going to start talking about unbalanced forces. First, we're going to head over to the lab, and I'm going to show you an example of Newton's second law to refresh our memories. Then we're going to head over to the classroom where I will describe the relationships between force, mass, and acceleration in Newton's second law. Then we're going to head back to the lab to see some more examples. Then we're going to head back to the classroom and I will show you all about free body diagrams for objects that are accelerating. What do they look like? So let's get started. Let's go. So now we're in the unit of unbalanced forces. And when we think about the difference between balanced and unbalanced forces, a really nice analogy we like to use is a tug of war. So in a tug of war, if both sides are pulling equally or if their forces are balanced, nobody is going to win that tug of war. However, if one side is pulling harder than the other, or if the forces are unbalanced, then somebody will win the tug of war and the tug of war will accelerate. And I'm going to show you right now with this handy simulation. So there is a blue team which is going to pull on the left and a red team which is going to pull on the right. The cart will measure the speed as they pull. And we'll also be able to see if the forces are balanced or unbalanced. So if the sum of the forces is 0, that means that all the forces are balanced on the system or on this cart here. So if I put one person on the blue team, you will see that that changes, that sum of forces, meaning we don't have balanced forces anymore. We have an unbalanced force that's pulling to the left with 50 newtons. So if I were to press go, we know that this cart would move to the left, and it would not only move, but it would accelerate to the left because there is an unbalanced force that's acting on it. Okay, there's nothing to oppose this force that's pulling to the left, so the blue team would win this tug of war and pull the cart to the left. But let's say I put a red person on the right team. Okay, now what do we notice? Now our forces are balanced. There's no force in either direction left over. Nobody's going to win this tug of war. So if I say go, both sides are pulling with 50 newtons of force, but no team is going to win. So what if I unbalance it though? So let's say I put a medium-sized blue person, okay? Now we notice that the small person is only pulling with 50 newtons. We knew that before, but now with the medium person also pulling, we notice that there's more left force than there is right force. Okay, so the difference there, if the left team is pulling with 150 newtons, the right team is pulling with 50 newtons, the difference there is obviously 100. So that would be the unbalanced force in this scenario, would be 100 newtons to the left. Okay, but I wanna have the red team win today. So I'm gonna choose the largest team member on the red side, and I'm gonna put them at the end of the rope. So now what do we notice? Well, it looks like these small people are pulling with 50 newtons on each side, so they cancel out. The larger person we found out was pulling with 100 newtons, but the medium person, I guess, on the blue team, the largest person on the red team is pulling with 150 newtons. So we have an unbalanced force here, right? So we can tell that not only from the size of the arrows, but also from the numbers. So we've got 150 newtons on the left, and we have 200 newtons on the right. So the difference there between left and right is 50 newtons. That's our unbalanced force. So the red team is going to win, which means they're going to accelerate this cart to the right because they are pulling with an unbalanced force to the right. So when I press go, we will see this cart move to the right. We will see it accelerate. So you will see the speed increase. So ready? Go. So notice how that speed is increasing. We have a change in velocity, which means we have an acceleration. So not only is the red team winning, or they won, but also that cart accelerated. Okay, so it's not just about which way something is going to move, it's which way something is going to accelerate. Okay, Newton's second law tells us that the acceleration of an object is directly related to the unbalanced force acting on it. So here we had the unbalanced force to the right, which means that the whole tug of war was going to accelerate to the right.
So as I just said in that example, the most important thing to remember about this unbalanced forces unit is Newton's second law. So Newton's second law tells us that the acceleration of an object is directly related to the unbalanced force that's acting on it. And that's a lot of words, but we like to remember our equation, F equals ma. So there's a lot of forces out there like Fg, Fn, Ft, Ff. So how do we designate this as the unbalanced force in the equation? Well, we're going to put a U next to our F. So our unbalanced force is going to be Fu. So Newton's second law is Fu is equal to ma, which is a little bit silly, but it helps us remember that that F is the unbalanced force. And of course we know that our m is mass and our a is acceleration. So we're going to talk about the relationships that we see between these variables in this equation. We know that the acceleration of an object is directly related to the unbalanced force acting on it. We know that because of Newton's second law, but what does that exactly mean? We're going to talk about that today. But this equation is going to guide all of our problems and all of our understandings for this entire unit because it's the equation that tells us about unbalanced forces. We didn't really need it last unit, but we really need it now. So there's two different relationships that we are going to talk about in terms of this equation. They're the most important relationships for this unit. So the first relationship is the relationship between the unbalanced force and the acceleration. So Newton's second law tells us that they're directly related, but it's been a while since we've talked about relationships. So what we're assuming here is that we're talking about the same mass, the same object. So when we change the unbalanced force, we know it's directly related to the acceleration, but what does that mean? Well, you might remember from the very beginning of the year, we talked about positive linear and negative linear relationships. A positive linear relationship, or a positive slope, is a direct relationship. So as one thing increases, the other thing increases as well. So as the unbalanced force increases on an object, the acceleration will increase as well, which kind of makes sense, right? The harder you push something, the faster it's going to accelerate. Similarly, as the unbalanced force decreases, so does the acceleration. So if you're not pushing something as hard, it's not going to accelerate. And that's a direct relationship. As one thing goes up, the other thing goes up. This other relationship is a little bit trickier. It's the relationship between mass and acceleration. So now we're assuming that we're keeping the unbalanced force the same, like we're pushing two different objects with the same unbalanced force. And the relationship that we find here is something different than a direct relationship or a positive linear relationship. What we find here between mass and acceleration is something called an inverse relationship. So we like to say that they are inversely related. We haven't talked about the inverse relationship. At the beginning of the year, we did talk about negative linear relationships, so like a negative slope. As one thing goes up, the other thing goes down. An inverse relationship is similar to that, not exactly the same, but we can kind of think about it in a similar way in our minds. So this inverse relationship between mass and acceleration, you can think of it like if you're trying to push a car and a semi-truck with the same unbalanced force. Well, as the mass goes up, the acceleration is going to go down, right? It's a lot harder to get something moving that has a lot of mass. Similarly, or conversely here, as the mass goes down, the acceleration is going to go up. So that's the other part of this inverse relationship. As the mass decreases, the acceleration will increase. So like if you try to push a feather with the same unbalanced force that you push a semi-truck, the feather is going to accelerate a lot faster. okay? So that's what an inverse relationship means. These are our two relationships. So the harder you push something, the more it's going to accelerate, but if it has more mass, the less it's going to accelerate. So we're going to see an example of this right now, actually. We're going to see an example of this in the lab. What does this look like for an object? Let's put these Newton's second law relationships into action. What I've got here is a skateboard with some physics textbooks on it. I also have attached a force scale to these textbooks. What I'm going to do first is illustrate the relationship between unbalanced force and acceleration. We know that the unbalanced force on an object is directly related to the acceleration that object has, which means the harder you pull something, the faster it will accelerate. So what I'm going to first do is I'm going to pull these textbooks with a force of 1 Newton. Then I'm going to pull them with a force of 4 Newtons. And I want you to note the differences in their acceleration based on how quickly they travel across the screen. Here's pulling with 1 Newton of force. That might have looked like it wasn't even accelerating, but it was, just at a very, very small rate. It was barely picking up speed as it was traveling across the screen. But let's notice the difference as we check out what happens when I pull these books with 4 Newtons of force. Not only did the textbooks travel a lot faster across the screen, but they were picking up speed faster too. They had a higher acceleration. But what about the relationship between mass and acceleration? We saw just how slowly these textbooks accelerated when I exerted a force of 1 Newton on them. But what if I get rid of most of these? What if I only pull one textbook with 1 Newton of force? We know that the relationship between mass and acceleration is inverse, which means as the mass goes up, the acceleration goes down. So let's take a look. I'm going to pull just one textbook across the screen on this skateboard with 1 Newton of force. All 5 textbooks together was about 12.8 kilograms, but only one textbook is about 2.6 kilograms. So a much smaller mass should result in a higher acceleration. So remember back how slowly the 5 textbooks accelerated. Let's see what it looks like when only one textbook is accelerating with 1 Newton of force. Now let's compare that to what we saw just earlier with 5 textbooks being pulled with 1 Newton of force. Here's pulling with 1 Newton of force. The next thing, or the last thing we really have to talk about today, is free body diagrams. So when we talk about free body diagrams, we're still going to use them in this unit because we're still talking about forces and they are still very important for us to be able to problem solve. So when we think about free body diagrams, last unit, when everything was balanced, well, all the forces were balanced on an object. So let's say you were trying to push your dining room table across carpet, okay? You're going to have the force of gravity because your dining table's on Earth. You're going to have the normal force because it's sitting on the ground, and you know those two things are equal and opposite because all the forces had to be balanced last unit. Then you had an applied force, to the right, let's say. You're pushing your dining room table to the right, but you're pushing it across carpet, which is a rough surface, so there's going to be friction that's pulling back, right? We knew, again, those forces had to be equal and opposite. That's not going to be the case in this unit. So in this unit, Unit 6, which is unbalanced forces, we're going to see that somebody is winning the tug of war. One of these forces, right? So it's either going to be friction or it's going to be the applied force, or it might even be like the normal force or the force of gravity, okay? One of those forces is going to win in this scenario and the object is going to accelerate. That's what we're going to see. So in Unit 6, there's a couple different situations that we like to think about, and I'm just going to show you and talk about their free body diagrams because they're not the same as this Unit 5 business. So we're going to put an X there through that, okay? Unit 6, though, again, we're going to star that because it's really important. There's 3 different scenarios that I want to chat about here. First, an elevator is accelerating up. So let's say an elevator is hanging supported by some cables. Well, it's on Earth, we've got the force of gravity, but if it's accelerating up, that means that the force that's pulling up has to be winning, right? It has to be accelerating the object up, and what's the force that's pulling it up? Well, we could call that the force of tension, like in those cables that's supporting the elevator, okay? So clearly the force of tension is winning because I drew the arrow bigger, okay? Our second example is a car accelerating to the right. Okay, so a car, we know it's going to have the force of gravity and the normal force acting on it, okay, as per usual. However, our acceleration is to the right. It's not up or down. So since our acceleration doesn't deal with up or down, then we know our normal force and our force of gravity have to be equal and opposite because the acceleration isn't happening in the up and down direction. It's happening left and right. So force of gravity and the normal force are going to be equal. However, there's going to be a giant force pushing to the right. We'll call that the applied force. Your foot on the gas pedal. You are applying that force to your engine. And then there's going to be a smaller force, maybe pulling back, force of friction, maybe some air resistance on your car. Okay, so that applied force is a lot bigger because the car has to be accelerating to the right. Okay, the applied force has to win the tug of war. Okay, our last example is an object slowing down due to friction. So let's say that object is sliding to the right. Okay, it's on a surface, it's on Earth, so we know we're going to have the force of gravity pulling down, and we know we're going to have the normal force pointing up. Similar to our car, those forces have to be equal and opposite because our object is going to be slowing down because it's moving to the right, so that's a different direction there. So up and down we have to be balanced. But we know that our force of friction points opposite the direction of motion. So let's say something is just gliding along the floor and it's coming to a stop, okay, because of friction. So friction is resisting that motion. So there's a giant force to the left. That's our unbalanced force. Our acceleration is to the left because we're slowing down. It's negative acceleration. We're slowing down. So again, we're going to come back to these free body diagrams. We're going to talk about each of these situations a lot more in depth. I just want to show you that in this unit, our free body diagrams are going to look different. They're not all balanced anymore, and we want to make sure that we label which force is winning very clearly. So in our first example, it was the force of tension. That arrow was a lot bigger. Okay, and then in the second example, our applied force was a lot bigger than the force of friction. And then in the third example, the force of friction was the big force left and right. There was no force to the right. Okay, so we'll be coming back to these. I just wanted to show you what our free body diagrams look like for Unit 6, Unbalanced Forces. Thanks for joining us. Today on Physics in Action. It's great to see you all again in the second semester. I hope you enjoyed learning all about unbalanced forces, how we represent them using Newton's second law, and in free body diagrams. Signing off for today, I am Miss Nielsen, Physics in Action.